In this session, let us try to understand load frequency control. Actually, load frequency control of power system and parallel operation of alternator is one and the same. Okay. Anyway, let me consider two alternators connected in parallel through tie line. Okay, so for example, okay, means mechanically all synchronous machines connected in parallel should be virtually mechanically coupled, we say. Okay, means I cannot in detail discuss about this because time is very less, but in brief I will tell you. For example, if I have two alternators connected in parallel, let us assume that this is going to be A conductor, B conductor, C conductor, and this is A, this is B, this is C. Okay, so this is A, B, C. Okay, for example, at one instant of time, if pole is here like this. Okay, at same instant, for example, if pole is here like this. Okay, then what will happen? For example, if pole is here, okay, so how much will be the induced voltage in A? 0. How much will be the induced voltage in A? Maximum. For example, if these two are connected in parallel, in the sense A is connected with A, B is connected with B, C is connected with C, okay, such that this is going to be A, this is going to be B, this is going to be C. For this, combinedly, if I connect the load, okay, so for this combinedly, if I connect a star connected load, for example, okay, so A is connected to A, C is connected to C, B is connected to B, then what will happen? At this particular instant, whenever phase A induced voltage is 0, phase A induced voltage is maximum, so maximum induced voltage to 0 induced voltage currents will flow. Okay, so normally in other machines except synchronous machines, we say that they are circulating currents, but in synchronous machines we should not call them as circulating currents, but we have to call them as synchronizing currents. Okay, because those synchronizing currents, for example, if it is happening when it is here, if it is here, okay, then what will happen? Huge rush of currents will flow, huge rush of bulk of power will be transmitted, such that this will become a generator, this will become a motor, such that it is forced to come to here. It is forced to come to here means that some torques will be developed. Okay, so some synchronizing currents or synchronizing torques will be produced if these two are not aligned. Means that under steady state conditions, if it is here, compulsorily it should be here only. Otherwise, our torques will come, those torques will make it happen. Okay, now for example, if it is rotating in this direction, what is phase sequence? As of now, A maximum, after that B maximum, after that C maximum, depending on the direction of rotation. Now for example, if it is rotating in opposite direction, what will happen? Let us see. For example, if it is rotating in opposite direction, first phase A is going to maximum, after that phase C is going to maximum, after that phase B is going to maximum. So what does it mean? Means as of now, whenever phase B is maximum, at the same instant phase C is going to be maximum. So huge rush of synchronizing currents will flow. So in order to operate them in parallel, compulsorily it has to rotate in the same direction. Okay, so for example, in order to complete one revolution, okay, it is taking X milliseconds. For example, in order to complete one revolution, this alternator is taking X milliseconds. In the same X milliseconds, it also has to rotate. For example, if it is rotating with in X milliseconds, if it complete one revolution, if it is taking more time, then what will happen? Again, instantaneous value variation, voltages variation will come. So synchronizing currents will come, synchronizing torques will be produced, synchronizing power will come into picture, such that bulk of power, electrical power is being transmitted between these two. Okay, and that particular electrical power will be converted into mechanical power. One machine will become generator, another machine will become motor, such that synchronizing currents will try to maintain synchronism among synchronously parallelly connected machines. Okay, so anyway, point here is very simple. Of course, lot of discussion is there, but for time being it is enough. Okay, so logic is very simple. If direction of rotation should be same, mechanically, virtually, direction of rotation should be same, speed of rotation should be same, okay, position of rotors with respect to one another is going to be same. So because of that, mechanically all synchronous machines are virtually coupled, we say. Okay, anyway, conclusion is very simple. If it is taking like x milliseconds to complete one revolution, it also should take x milliseconds only to complete one revolution. Okay, so if it is creating like one cycle here induced voltage, it also has to create one cycle only, then only we can say they are operating under steady state condition. Otherwise, because synchronizing currents or synchronizing torques are going to be transient condition. Okay, so under steady state condition, operating frequency of this and operating frequency of this should be same. Okay, now for this alternator, prime mover will be there. Okay, prime mover will be there, and for this alternator, prime mover will be there. Okay, I discussed previously like in induction motor harmonic section. Okay, in induction motor harmonics we solved one problem. Compulsorily you have to go through it. Okay, because it's going to be most like damn good question. Now anyway, there I clearly told that like in induction motor, time harmonic has to be considered. In no other machines we consider. And similarly in alternator, speed control, like speed regulation, I'm sorry, it's not speed control, speed regulation of prime movers has to be considered, because means we have huge weight. Okay, so all over India thousands of alternators are there, thousands of prime movers will be there. So speed regulation of prime mover has to be considered. In no other generator we consider. In DC generator we don't consider speed regulation of prime mover, but anyway you have to consider here. For example, prime mover 1. Okay, so prime mover 1, if you keep on increase the output, okay, so if you keep on increase the power taken by this, means electrical power or mechanical power, power is power. Okay, so if you are extracting more power because of the speed regulation of prime mover, it is no way concerned with the alternator, it is concerned with the prime mover. Okay, so depending upon the prime mover speed regulation, depending upon the output, this is going to be omega r of like prime mover. Okay, so it is going to means my speed is going to reduce. Okay, now what we have to do, basically this is mechanical speed. Okay, so mechanically speed is going to be reduced. Now in electrical terms we have to convert into some other terms, because we are electrical engineers, and let us map this from mechanical domain to electrical domain. Okay, if speed reduces, actually one great interview question is there, like if speed reduces here, magnitude of voltage will be reduced here, and also frequency will be reduced. Okay, because if speed reduces here, okay, then induced voltage generated here will be reduced, no? And if speed reduces here, frequency also will be reduced. Okay, now interview question is like they will ask you why we consider frequency variation only, means why not like voltage variation. Okay, means answer for this interview question is very simple. Automatic voltage regulator will be there. Okay, so because of automatic voltage regulator, field current will be automatically adjusted such that terminal voltage will be maintained constant. In a sense, for example, if prime mover speed is reduced because of increase in output power, if prime mover speed is reduced, means that generated voltage here will be reduced, but that generated voltage reduction will be auto compensated by increasing field current. Okay, but if you think of frequency cannot be compensated. Okay, so basically because of presence of automatic voltage regulator or field current variations, this particular mechanical speed variation will be converted in terms of frequency only, not voltage. Okay, so means my frequency of generated voltage is going to be reduced depending upon this. Okay, now if I think of like synchronous machines. Okay, basically in synchronous machines, two machines connected in parallel will be there, or one machine connected with infinite bus will be there. Okay, so let me repeat again multiple times, like in stability we analyze the same, and in faults also we analyze the same. So two alternators, it's not like transformer, it's not like DC generators. Let us consider, even I have seen like in few videos. Okay, so parallel operation of alternators, people are connecting like 10 alternators, 5 alternators. No, only 2 alternators will be there. Now you may think of, no sir, like we are having thousands of alternators connected in parallel in the physical world, but why, how can you say only 2? No, I'll take only 2. Why? Because as usual, like our previous analysis only, for example, this is my small incoming alternator. Now I would like to analyze this alternator. Now remaining all alternators I am going to convert into equivalent one alternator. Okay, so my focus is here. So there will be nothing like, in parallel operation of alternators, three alternators connected in parallel, 5 alternators connected in parallel will not be there. Analysis will not be there, because if I want to analyze this alternator, remaining all alternators are synchronous machines connected in parallel, means equivalently I am going to convert into one. So one alternator connected in parallel. For example, if stiffness is so high, okay, such that my incoming alternator is there under steady state. I repeat, under steady state. Now incoming alternator is there, and thousands of alternators are there connected in parallel. Under that condition, these thousands of alternator mechanical inertia can be assumed as infinite, and such that alternator connected with infinite bus can be considered. So in parallel operation of alternators or load frequency control, only two conditions should be there: two alternators connected in parallel, or one alternator connected with infinite bus only will be there. Okay, so for example, let me think of infinite bus first. Actually, we are going to analyze this problem very soon, and beautiful, very beautiful 3 problems we are going to analyze. Anyway, for example, only 2 alternators, no? 2D. So for example, this is going to frequency, this is going to the power output of alternator A. Okay, now for example, this is going to be the frequency reduction is nothing but speed regulation of prime mover. For example, if it is about to be connected with infinite bus. Okay, so in infinite bus, whatever may be the infinite bus power. Okay, so frequency, will it reduce? No, because infinite bus, no. Okay, thousands of alternators equivalent I consider as infinite bus. Under that condition, okay, so this is going to be, for example, this is 50 Hz. Okay, so first of all, my incoming alternator, you are about to synchronize with infinite bus at 50 Hz. Okay, synchronization procedure will be there, forget about it, problem cannot be formed from there except theory question. Okay, so anyway, for example, your incoming alternator is synchronized with infinite bus at 50 Hz. Now what you have to do, you are supposed to supply your power. Now what is the purpose of your alternator? Your purpose of your alternator is supposed to be means you are supposed to sell your power. Then what you have to do, governor will be there. Okay, so governor setting will be there. This is frequency. So governor setting will be there. With governor setting, what I will try to do, I will try to map the governor setting. Okay, if I try to map the governor setting, okay, so about governor setting and all, it take much time, detailed course. Okay, so if I change the governor setting, then with infinite bus, how much power I'll be able to supply to infinite bus? This much power I'll be able to supply. Okay, for example, if I change the governor setting again, it can go up to here, such that rated power can be sold. Okay, so point here is see here, the conclusion is very simple. You can have your drooping characteristics of depending upon speed regulation of prime mover, drooping characteristics in frequency will be there. Okay, so the drooping characteristics in frequency, once it is connected with infinite bus, you should not say means how to supply power. We are having governor setting. So if you change the governor setting, automatically, for example, if you change the governor setting to here, this much power you can sell. If you change the governor setting again, rated power you can supply. Okay, so by changing the governor setting, you are going to supply power. Okay, to infinite bus. For example, if I have 2 alternators, as I told you, only 2 cases will be there. 2 alternators connected in parallel, 1 alternator connected with infinite bus. Okay, so for example, if I have 2 alternators, okay, so this is PA and this is PB. Okay, so one alternator is like this, drooping characteristics. Another alternator may be like this, drooping characteristics more. Under that condition, as all synchronous machines are virtually mechanically coupled, frequency should be same. Okay, so for example, if this is frequency, okay, so this machine is going to supply this much amount of power, this machine is going to supply this much amount of power. Okay, now for example, actually one doubt will be there to the students, students feel this drooping characteristics is more, this drooping characteristics is less. That's why it is supplying more power, it is supplying less power. No. No. For example, economic load dispatch problem is there, right? So in economic load dispatch problem, maybe whatever is having more grouping characteristics can be hydro station. Whatever is having less grouping characteristics can be steam turbine. Then you have to give more preference to hydro, no, as a base load plant. Okay, so under that conditions, what I am supposed to do, don't think whatever is having less drooping characteristics, less slope means it is supplying more. No, it will not be like that. I'll have, got my point, right? So speed governor setting will be there. If I have speed governor setting, okay, under that conditions it can supply more power, it can supply less power. Okay, so don't never ever think that in the drooping characteristics, whatever is having more drooping will supply less power, whatever is having better slope, okay, or less speed regulation will supply more power. Should not be there, because we have governor setting. Okay, so now we can start solving problems. Okay, so we are going to take 3, which is first is at no load condition operating frequencies are same. Second problem is at full load condition operating frequencies are same. Third one is given in old gate. Beautiful question. Now anyway, let us consider this. 2 identical 2000 kilowatt alternators are in parallel. Okay, the governor of the first machine is such that frequency droops uniformly from 50 Hz on no load to 48 Hz on full load. The corresponding uniform frequency droop of second machine is from 50 Hz to 47.5. How will the two machines share a load of 3000 kilowatt? Okay, so for example, these are 2 alternators connected in parallel. Okay, so this is going to be 50 Hz. For example, this is 2000, right? Yes, this is 2000 kilowatt, and the other machine is also 2000 kilowatt, he is saying. Okay, so this is also 2000 kilowatt. Okay, so this is machine A, this is machine B, and machine A is drooping from 50 Hz at no load to 48 Hz. So 50, this is load, no? This is going to be PA. Okay, so at no load, how much is the frequency? 50. At full load, it is going to be 48. So this is 48 Hz. What do you say? Okay, and second machine is saying the corresponding uniform frequency droop of second machine is 50 to 47.5. So 0 Hz, 48, 50, 100, like that. So 47.5 should be below this. Okay, so this is going to be 47.5 Hz. So drooping characteristic is going to be like this. Now combinedly, because frequency of operation should be same under steady state conditions. So for example, this load, this is operating at some frequency f. This load is how much they have given? 3000 kilowatt. 3000 kilowatt. Done. Problem solved. Okay, now we have to follow the slope characteristics. That's it. Okay, so if you follow slope, you will get the answer. Okay, so for example, if any characteristic is there, okay, for example, this is the characteristic. Now actually ideally the speed regulation characteristic is non-linear. Okay, for our better to simply calculate the things, because we are at UG level, okay, not at research level. So that's why they'll make it linear. Okay, for example, from here to here slope is something, from here to here also slope is same, from here to here also slope is same, from here to here also slope is same. That's it. Okay, so for example, what is slope? Dy by dx. Okay, so dy frequency change by dx power change. Okay, so actually many guys have doubt here. Focus. Now what is frequency? Of course slope is negative, I know. Okay, so dy 50 to 48, 50 to 48 y-axis is giving x-axis variation of 2000. Okay, so equation is going to be 50 minus 48 by 2000 dy by dx. 50 minus 48, okay, 50 minus 48 by 2000 is going to be this slope. Now the same slope should be there between 50 and F now. The same slope should be there between 50 and F, right? So 50 minus F divided by, what is this? Let us call this as PA. PA. Right? Now let us think of the other side. Let me call this as PB. What is PA plus PB? 3000 net output. So 50 minus 47.5 by 2000 dy by dx slope equal to 50 minus F divided by, what is PB? 3000 minus PA. Problem solved. Okay, actually this is easy to calculate because this divided by this will be cancelled. Okay, so this divided by this, if I do 50 minus 48, 2 divided by 2000 into 2.47.5, 2.5 by 2000 equal to 50 minus F, 50 minus F will be cancelled. PA 3000 minus PA. That's it. Okay, so in upcoming problem situation will not be like this. Okay, in upcoming problem you have to calculate two equations. Anyway, we will see immediately after this. So how much is PA? From here I calculated, I got PA of 1666.67 megawatt or kilowatt, and PB is going to be 3000 minus that is going to be 1333.33 kilowatt. Problem solved.